This is a black hole. We imagine it as a huge, ultra-dark region in space that pulls everything in. And once something falls inside, it's dragged to a final point called a singularity. But what if we told you that black holes don't work quite like that? So what exactly is a singularity? And what truly lies in the pitch-black darkness and beyond the veil? Get ready to discover the dizzying world of black holes, where reality is far scarier than any fiction. Black holes are complex cosmic phenomena formed when a large star, about 10 to 20 times more massive than the Sun, exhausts all its fuel. The balance between gravity and pressure collapses, and the star implodes into a supernova. The problem with our current understanding is that we use different theories to explain events on different scales. There's quantum field theory, which explains the complex behavior of particles, from atoms to the tiniest building blocks of matter. But when applied to astronomical scales, it becomes useless. For that, scientists turn to Einstein's general theory of relativity. Choose the right theory and the math works. But with black holes, it's not so straightforward. These objects start as massive stars and then quickly collapse into something much smaller, sometimes on a quantum scale. For example, to turn the Sun into a black hole, it would need to shrink to a radius of about 2.5 kilometers. In theory, any object could become a black hole. There's a formula that tells us how dense something needs to be to reach that state. This threshold is known as the Schwarzschild radius or gravitational radius. If you're wondering how small Earth would have to be to become a black hole, imagine compressing the entire planet into a sphere just 0.88 centimeters in radius. But what if the object's radius becomes zero? Traditional physics and mathematics break down, and none of our current theories can describe what's happening. Could such a black hole actually exist? Consider a thought experiment. To create the simplest version of a black hole, you'd start with tiny bits of matter floating in space. They're not touching anything, just suspended there. These are like tiny dust particles floating close together but not moving. But gravity exists in space and starts pulling everything together, reducing the space between the dust particles. Over time, the dust compresses more and more until their combined mass and gravity becomes so intense that space around them begins to collapse. This creates an event horizon, a kind of boundary that lets things in but doesn't let anything out. This type of black hole is called a Schwarzschild black hole. It has a point-like mass, meaning it was formed entirely from compressed matter, but it has no electric charge or rotational motion. Now, imagine what happens if you cross the event horizon of such a black hole. For the sake of the experiment, suppose it's big enough for you to enter with a spaceship. Once inside, you panic and try to escape, firing up engines to accelerate out. Physics says no matter which direction your ship faces, you'll still be pulled toward the central singularity. Imagine a long, narrow corridor with no exit except a door at the end. Once you enter the corridor, the door locks behind you, and there's no way to reopen it. Inside is a moving walkway, like those in airports, rushing forward at the speed of light. No matter how you try to move, either running in the opposite direction or with it, you'll still be carried forward. That's essentially how scientists think black holes work. But space-time becomes much more complicated when you introduce a rotating mass. All known black holes so far have angular momentum. They form from the collapse of massive rotating stars, and the rotation is preserved as the matter collapses, leading to a spinning black hole. Quantum mechanics was developed to explain the bizarre world of very small scales, but instead of providing answers, it introduced even more uncertainty, like fluctuations in space-time itself. And these quantum fluctuations play a significant role at the event horizon. We've all heard that nothing can escape a black hole, but things get trickier. Near the event horizon, particles and antiparticles spontaneously appear and annihilate almost instantly. But what if one of them manages to escape the grip of the black hole? The late, great Stephen Hawking explained this in his theory of Hawking radiation. When a particle-antiparticle pair forms near the event horizon, one falls in while the other escapes, stealing energy from the black hole in the process. And here's where it gets interesting. According to Hawking's theory, a black hole could evaporate over time, leaving nothing behind. But if a black hole leaves nothing, where does that infinite singularity go? In the early universe, infinities didn't exist, or at least we haven't found any yet. So when scientists get results that involve infinity, it usually means the theory is flawed. It's too simplistic to apply to extreme cases. Picture a guitar string gently plucked at a resonant frequency. According to the simplest model, its vibration would grow exponentially, eventually vibrating past the moon and stars to infinity and back. But that's not what really happens. The presence of infinity in the model shows it's an oversimplification and that there's actually a limit. So what does this mean for our understanding of black holes? If singularities aren't real, maybe at the center of each black hole lies something entirely different, something beyond our full comprehension. But as always, scientists have ideas. According to Penrose's theorem, a singularity is inevitable in general relativity. Anything moving through space under gravity must follow a specific path. This is called a geodesic. It's essentially the shortest and most efficient path through space and time. The idea is that all space-time is structured this way. The universe is one giant fabric, shaped by these geometric lines, some straight, others curved. These paths are infinite, like a line traced over this object. But Penrose proposed that inside black holes, geodesics must end at a single point, meaning the very paths of spacetime come to a halt, creating a singularity or infinity. Stephen Hawking believed this is how the Big Bang began, as a singularity, or in other words, geodesics converging to one point. However, recent research suggests a different view. In rotating black holes, the spinning matter changes everything. Instead of a single event horizon as a boundary, spinning black holes have two, an outer and an inner horizon. These horizons act like invisible walls marking regions where gravity becomes increasingly strong, until it's too strong for even light to escape. Rotating black holes also have a so-called ergosphere, a twisted region around them where spacetime itself is dragged along faster than light. If you were inside it, no matter how hard you tried to remain still, it would be impossible. In a way, these spheres are like whirlpools in spacetime, influencing how objects move. Nearby objects rubbing against each other emit incredibly bright light. Due to how insanely fast everything moves there, if an object escapes the ergosphere, it can come out with far more energy than it entered with. In theory, this mechanism could be a source of nearly unlimited energy, though extracting it is nearly impossible. But again, the singularity still exists. Though a black hole doesn't have a point-like shape, it instead forms a ring structure due to the effect of angular momentum, which smooths out the singularity. Here's a way to visualize it. Imagine a drop of paint falling on a sheet of paper. If the paper is still, the drop forms a point. But if the paper spins rapidly, the drop spreads out into a ring. So, if material falls into a black hole along this twisted path, its trajectory won't be a simple circle in one plane. Instead, it moves everywhere. Over time, the particle's path becomes three-dimensional. So, rather than following a flat path, particles around spinning black holes move in all directions, tracing a kind of ring in space. These particles don't just cross the event horizon and go straight to the singularity. It's not like dropping a rock into a pond where it sinks straight down. Instead, it's like tossing a leaf into a strong wind. It gets blown in all directions. Sometimes the wind pushes it downward, sometimes lifts it up. In the end, spinning black holes don't have true singularities, those mathematical points of infinite density. Inside, beyond the event horizon, gravity creates a unique spacetime around the ring-shaped singularity where objects can move in various directions. Geodesics can exist there for a very long time. So what is this ring? It's a gravitational field caused by rotating particles inside the black hole. And here's a fascinating fact. The matter that formed the black hole is still inside this dark monster. Bits of the star that formed the black hole continue moving along their paths and can exist there for a long time. Even light can exist in this place. Imagine it as an almost infinite carousel, cut off from the outside universe, lit by a strange glow. What do you think about this new perspective on black holes? Share your thoughts in the comments. We hope you enjoyed the video. If you found it interesting, don't forget to like and subscribe.